Last month, scientists announced a major breakthrough.
Today, astronomers unveiled the first ever picture of a black hole.
It made headlines around the world.
It's like looking at the gates of hell, the point of no return.
This month on The Sky at Night, we meet the people behind the Event Horizon Telescope to find out how this amazing image was captured.
We'll be discovering what this image can tell us about the most powerful monsters in the galaxy, supermassive black holes. Found at the heart of every galaxy, supermassive black holes have the power to tear stars apart. They emit powerful jets that travel for light years through space. And they may be able to tell us about the early universe and how galaxies are formed. Welcome to The Sky at Night.
At the beginning of April, a research group called the Event Horizon Telescope summoned the world's press to Washington, D.C. We knew that for 10 years, they'd been trying to take a picture of a black hole, and now they were going to make a major announcement. This is a really unusual press conference because although we know that there's an announcement coming, we've got no idea what it is that the team want to show us. If it lives up to some of the hype, then it's going to be really exciting. We didn't have long to wait. At just after 9 in the morning, the EHT director, Shep Dolleman, took to the stage.
And we are delighted to be able to report to you today that we have seen what we thought was unseeable. We have seen and taken a picture of a black hole. Here it is.
Well, here it is. Here's the image. It's really, really quite something to see this. You've got the shadow of the black hole itself here. They've just said that the light drops off really steeply, just like you'd expect for a proper black hole. You can see the bright material, that's light that's just escaped falling in, and it's brighter down here than on the top. And we think that's because the black hole's rotating. But there's so much more to learn from this image alone. It's going to be really exciting to work out how this black hole behaves.
This is an amazing picture to see, especially when you consider that as recently as just 50 years ago, people didn't think that black holes could exist. They were just a strange mathematical aberration of Einstein's theory of general relativity. According to Einstein's theory, space is made up of a fabric called space-time. That fabric is deformed by mass. The denser the mass, the more space-time stretches. Until when it becomes so dense that a star the size of our sun will be just 2 miles across, it creates a hole in space-time that is infinitely deep. A black hole. And it has a colossal gravitational influence on the space around it. Imagine a boat sailing near a black hole. If it's far enough away from it, it can sail past without even knowing it's there. But if you get close enough to feel the pull of its gravity, then getting away becomes a lot harder. And there's an invisible line that surrounds a black hole, known as an event horizon. Anything that passes this gets sucked into the black hole and disappears forever. Not even light can escape. A black hole is completely dark. Since light cannot escape the event horizon, we can never know what's going on inside it. We could never photograph the black hole itself. But as material is pulled towards the event horizon, it swirls round the black hole and forms an accretion disk. As it swirls inwards, the material in the disk reaches enormous speeds and heats up to millions of degrees. And as it does so, it starts to shine. It becomes one of the brightest things in the universe. And it's this glowing material in the accretion disk swirling round the black hole that the Event Horizon Telescope photographed.
Back in Washington, to find out what the image shows us, I grabbed a few minutes with the leader of the EHT team, Shep Dollerman. Well, thanks for finding time on a quiet day to talk to us.
Not so quiet, but a pleasure.
Yeah, I think the result is the image, which we've got here, but I know you've spent all morning staring at it. It really is
I can't stop looking at it.
It is well, I've had the same reaction. It's beautiful. What are we looking at here? What's the geography of the image? What are we seeing?
So this is the last photon orbit, right? This is where light is forced to orbit in a circle around the black hole. And the reason you see this dark patch in there is because that's where light crosses the event horizon and is lost forever. It's the combination of these two, the contrast of the bright ring and the dark shadow, that gives rise to this silhouette feature.
Why is it brighter at the bottom?
So the brightness at the bottom occurs because the gas moving around the black hole is moving at near light speeds. And when gas moves so quickly, most of the emission that comes from it is focused in front of it, in the direction of motion. So you're seeing light from gas that's moving below the black hole coming up like this, and it's much brighter. Here you're seeing gas moving away from you, so it's dimmer.
It gives you a real sense of a physical thing, not a mystery, but a thing with spin and that's moving.
Absolutely. You know what, I have to say, I'm astonished and astounded by how wonderful and true that image is. I was fully prepared to see a blob, because there's so many ways it could have been a blob. The Doppler boosting of the light speed motion of the gas could have made one part much brighter than other parts. It could have dominated.
Well, then you just see that.
And all we would see would be a bright spot. And we wouldn't even know, is that in the center where the black hole is it off to the side? There's something might have gone wrong with our instrumentation, but everything would have pointed to an indiscriminate, blobby thing.
Why is getting this image important?
Well, it's always important to go to the most extreme laboratories to test our theories, right? Because we know that things begin to break down in the most extreme laboratories. So it's one thing to test gravitational theories here on Earth.
Or in the solar system.
Or in the solar system, or near a neutron star. But black holes drive large-scale structure in the universe. In a paradox, they're the smallest things that Einstein predicted, but they have these effects that can span across entire galaxies. And then there's the unknown. This is the only place in the universe where you go, but you can't come back. And knowing that there are monsters out there, and that we can take pictures of them, that we can start to tame them a little bit, is, I think, very compelling.
This is just the beginning. That's the point, right? Yeah. This is the start of doing science this way, not the end.
I refer to this as the end of the beginning, right? Because we've laid the groundwork, we've proven the concept, now we have a lot more work to do, but it's not the end.
All right, well, we'll let you get on with it. Thank you very much. Congratulations. Talk to you soon. It's truly amazing to be looking at an image of a black hole. Though it's important to realize that the dark circle that we see is not the black hole itself. It's just its shadow. The gravity of the black hole is so strong that it affects all of the photons of light that travel near it, curving their paths across the event horizon, creating a hole or a shadow in the observation. The shadow is about twice the diameter of the event horizon, which is believed to be about the size of our solar system. That makes it sound as if the black hole is a giant object. But on cosmic scales, it's tiny. And capturing this image has been a remarkable technological achievement.
One of the most important things the team needed to do was to choose a black hole to photograph. In theory, there should be no shortage of black holes to choose from. We think there are billions of them out there, but the problem is we don't know where most of them are. The vast majority of black holes, so-called stellar mass black holes, are tiny. They are typically 10 to 30 times more massive than our sun. but are only a handful of miles across, no bigger than the average city. Picking out these tiny objects in the vastness of space would be all but impossible. But luckily, there is another class of black hole. These are pictures of stars moving around the very center of our galaxy. It was taken over a period of 16 years. The stars move in tight elliptical orbits with colossal speeds of up to 25 million kilometers per hour. It's as if something at the heart of our galaxy is moving stars around as if they were toys. The only thing that can cause this is something with a massive gravitational influence, a black hole. But a black hole with a mass more than 4 million times that of our sun. A supermassive black hole. The black hole at the heart of our galaxy is known as Sagittarius A star. And it is not alone. We now think there's a supermassive black hole at the heart of almost every galaxy. One of the most spectacular is found in galaxy M87. We know there's a black hole there because it generates huge jets that extend over 4,000 light years through the galaxy, as seen in these dramatic images from the Hubble Space Telescope. The M87 supermassive black hole is 55 million light years away from us. That's 1,000 times further away than the supermassive black hole that sits in the heart of our galaxy. But M87 is also 1,000 times bigger. That's 6 billion times the mass of our sun. So this is the supermassive black hole that the EHD team decided to image. To find out how they did it, Chris met up with imaging scientist Katie Bowman.
We've seen this amazing image, but people will think maybe that that's what you get sitting at the telescope. Actually, there's a lot of work that goes into it.
Yeah, it's been a long process that, we also have to do very carefully that has taken a lot of time. So actually, we took these observations exactly 2 years ago today. And it's been a long process of not only taking the observations, but processing it down to data that we can then make an image and then validating that image to get you the image that we were able to present to you today. The M87 black hole is so small and so far away from us that it is the same size as if we were trying to take a picture of an orange on the surface of the moon. And at the wavelengths that we need to pierce through all the other stuff that is around the black hole and see that shadow, it turns out that just by the law of diffraction, we would need a telescope that is the size of the Earth.
To build their Earth-sized telescope, the EHT recruited 8 radio dishes spread across the globe. From Europe and North America to Chile, Hawaii, and even the South Pole, they made a network over 10,000 kilometers across. Just over 2 years ago, all these telescopes lined up on the heart of the M87 galaxy, and synchronized by atomic clocks, they began their observations. The dishes collected millions of gigabytes of data that were delivered to Katie, who with the other imaging teams would try to put it all together to produce a single image of the black hole.
So the reason the problem is so hard, and obviously then it also makes it a lot of fun, is the fact so it's very sparse data, right? We have only had a few telescopes. It's incredibly noisy, noisier than most other data.
Because the thing you're looking at is faint, right?
Well, it's faint, but also we lose a lot of information because the atmosphere affects the light that we measure. And so what we have to do is come up with algorithms that not only say, okay, what image matches that data, but what image is most likely to have caused this data. We put together this script and we pressed go, and amazingly, I was like in disbelief. This ring started coming into focus, and that was an amazing moment. It was just, I was in disbelief.
And so what we've seen today is the most likely image that matches the data that the telescopes received. Is that fair?
Sure. Well, I mean, it's not the full story, because actually we don't want to just come up with one algorithm and one definition of likely. We've come up with many different definitions of likely, and the image that you saw today was a combination of different images, blurred to the level that we thought got all of these results agreed to.
And now you've shared it with us. So thank you for the hard work and thank you for the image.
Although this image gives us our first view of a supermassive black hole, we still know surprisingly little about them. We do know that they sit at the heart of nearly every galaxy, but we have no idea how they got there or how they were formed. We think stellar mass black holes, the millions of smaller black holes that are found throughout every galaxy, are formed by the death of giant stars. Stars are continually fighting against gravitational collapse. For most of their lives, energy provided by nuclear fusion happening in their core counteracts this tendency to collapse. But when they run out of fuel, they cannot resist the strength of their own gravity. As the stars stop burning hydrogen, they start to fuse other elements and swell up to an enormous size, before they suddenly collapse. Stars the size of our sun will collapse down to a white dwarf, a super dense remnant about the size of the Earth. But the death of bigger stars, 10 times the mass of our sun or more, is much more dramatic. They collapse in on themselves so violently that they rebound in a massive explosion called a supernova. But inside the supernova, the core continues to collapse, falling in on itself until the whole mass of the star is compressed into a single infinitesimal point. A singularity, the core of a black hole. The death of giant stars is the only mechanism we know of that can create black holes. But that can't explain how supermassive black holes, millions or billions of times the mass of the sun, are formed. As Chris discussed with astrophysicist Jana Levin.
How would a black hole like this one have formed in the first place?
So that's an unknown problem. It's an unsolved problem. So we don't think that they form from stellar collapse like most of the black holes we know about, because they tend to be in the 10 times the mass of the sun, 30 times the mass of the sun. It would take a lot of those, millions or hundreds of millions of those, to make something that big, or thousands of millions to make something as big as the one in M87. And there really isn't enough time for them to just merge, collapse together. And so some people think maybe they formed in the very early universe out of very large stars that collapsed, or maybe they just directly collapsed out of a primordial cloud and skipped the star altogether.
So this could be a very old object we're looking at.
Oh, it could be a very old object.
The reason that we think supermassive black holes were formed in the early universe is because we know that some of them, known as quasars, are very ancient. Quasars are powerful beacons that shine with the light of trillions of stars. They're so bright that we can see them right across the universe. This tiny red dot is one of the most distant quasars we've ever observed. It's so far away that the light from it that we're seeing now has been traveling across space for more than 13 billion years. It means that this supermassive black hole was blazing away just 700 million years after the Big Bang. And if all supermassive black holes are that old, then it's possible that they played a role in the evolution of the entire universe. So, why are supermassive black holes like this one important? You know, that if you were telling the story of the universe, you wouldn't think you'd need to mention these tiny things at the centers.
Well, interestingly, most stellar mass black holes, most black holes that we know are formed from the dust states of stars, aren't that influential in the universe. They're just incredibly bright, so they're interesting in that way, but it's the supermassives that actually influence the universe. They sculpt the way a galaxy is formed, and it may well be that they regulate the shape and size of galaxies.
People will be surprised to hear that,
Yeah.
because black holes are things from which nothing can escape.
Yeah.
And yet here we are talking about light around a black hole and them influencing their galaxies. How does that work?
It is a kind of a great irony that the darkest phenomena in the universe, the one that is literally exactly dark, becomes the brightest beacons in the universe. And it's just because you can mine the gravitational power when you influence things around you. So black holes just cause mayhem in the stars and debris and anything that comes close. around them, and that stuff's luminous, and the black hole becomes the engine for that. It becomes the engine for turning things up. So the black hole itself remains dark. None of the light, the jets, all of this stuff we're talking about does not emanate from within the black hole. It all happens around it.
And it's understanding the physics of that, which is
Yeah.
one of the reasons we
Yeah.
do experiments like the one we've talked about today.
Yeah.
So do you think we'll get a better image than this one day? Will we see further into the black hole?
Yeah, I think we'll get more detail. I know that they're adding more telescopes to the network, and that will be interesting. And it's conceivable to make a telescope even bigger than the Earth if we go to space. And I don't know what the ambitions are for space, but if that happens, we could also see it evolve over time and get movies, not just these instantaneous snapshots. It might be, though, that we never get in any closer than the last place a photon can safely orbit, because the light just doesn't want to come out.
I don't know, amazing thought to think
Yeah.
we've seen the edge of something that we
Yeah.
won't see further in than that.
Yeah, not unless you want to go over there.
All right, thank you for talking to us.
It's fun.
Cheers.
The Event Horizon Telescope is one of the most impressive technological feats of modern astronomy. But there are also ways for you to contribute to pioneering black hole research, as Pete has been finding out.
You might suspect that black hole research is solely the realm of the professionals, but in fact amateur astronomers are playing their part too. Tonight I'm at Rutland Water Nature Reserve, and I'm joined by an old friend of the show and a member of the British Astronomical Association, Dr. Paul Abel.
So Paul, thank you for joining me here in this rather wonderful location.
A bit cloudy tonight though, Pete. Not terribly good.
No, we didn't get any luck there. So how can amateurs actually contribute to black hole science?
Well, it actually starts out with the British Astronomical Association, which was founded in the 1890s, and they have a variable star section, which is concerned with collecting observations of stars whose light appears to vary. But not all of those things are stars. Some of them are black holes. In particular, we have the beautiful system 𝐭𝐥287, which is a binary black hole system, so very exciting.
A binary black hole system consists of two black holes in close orbit around each other. And it's one of these systems that the BAA is asking amateur astronomers to observe.
Now, a very common question that's asked when you want to observe a black hole is, how on earth can you observe it? It's black, for goodness sake.
That's right. And they don't emit any light. And the answer to that is, it's the immediate environment of the primary black hole that's the answer here.
Okay.
There is an accretion disk that's orbiting the black hole. So this is hot gas and dust that's circling around.
Right.
And what happens is the secondary black hole punches through this material. And as it does that, it destabilizes this accretion disk and causes it to brighten up enormously. And that's what we're actually observing.
If you're interested in joining the BAA survey, then you'll find 𝐭𝐥287 in the constellation of Cancer. It's 3.5 billion light years away and consequently rather faint. To find it, locate the two stars Ocellus Australis and Ocellus Borealis just by the Beehive cluster, Messier 44. Form an equilateral triangle pointing away from the Beehive cluster, and 𝐭𝐥287 is right at the tip. You'll find all the information on how to take part in the survey online.
This is from the BAA website. This is a finder chart. You can go to the website and download it.
Yeah.
It shows not only the location of 𝐭𝐥287,
Yeah.
but the comparison stars of fixed magnitude. And what you do is you compare the brightness that you can see of 𝐭𝐥287 with these standard stars and make your magnitude estimate. If you go on the website, it gives you tutorials how to actually make magnitude estimates.
So how often would you make those observations to get meaningful data?
I think every clear night. And then what you can do is we've got the magnitude plots on a graph here, and these are all individual amateur observations which generate this light curve.
Is this actually real data?
Yes, absolutely.
Wow.
And this is a way of amateurs to contribute to black hole science, and I think it's very exciting what was once considered sort of very esoterical, strange astrophysical objects. Now we can study them from your own back garden. Isn't that wonderful?
That's fantastic. So what have we learned so far about this system?
Well, we've learned quite a bit already, so things about the accretion disk and about how the black holes orbit each other. But I think the most useful thing from our point of view is it allows us to predict future events. So we had brightenings in 2005 and 2007, and the next big one, the next big disk event, is on the 31st of July. But unfortunately, the sun is almost in the constellation of Cancer, so it's in conjunction, going to be very difficult to observe. But the Spitzer telescope, which is quite a distance away from Earth, will be observing the event.
The Spitzer will fill in the gap which we can't see.
That's right, but amateurs will then contribute observations before and afterwards. With the Spitzer data, we can then piece together the whole narrative of this system and provide an overall symphony of observations, Pete.
Very poetic. Thanks so much, Paul.
Thank you, Pete.
Back in Washington, amongst the croissants and the coffee, there was palpable excitement amongst the scientists that the Event Horizon Telescope would soon start to reveal the secrets of supermassive black holes, especially those spectacular jets that can extend for thousands of light years. Can you explain what a jet is and what we mean by powering something?
Yeah, well, so basically they're just like fire hoses of material.
Moving very fast.
Moving very fast, and we can see how fast they're moving. We can actually measure this, and in some cases they look like they're moving faster than the speed of light, which tells us that they have to be moving close to the speed of light, and it's a kind of special relativistic effect. So we know they're very fast. We can measure their power by looking at the multi-wavelength, for instance, and you'll see these cavities that are inflated by the jets, and that's a way of calibrating the power.
So really the scientific question here is, where is it that the jet's starting? Is it a little further out, or is it right in at the regions that we're now probing?
And from everything that we can see, not just from the Event Horizon telescope, but other observations, it seems to us that the jets are being launched very close to the black hole. From the Event Horizon, we combine that with models of what we saw. We haven't published this yet, so we're sort of moving in that direction. But our general sense is that we cannot power the jets that we see without this extra bonus of tapping the black hole's spin.
What will understanding black holes like this tell us about the galaxies that they live in?
So we've known for a long time that something has to affect the galaxy growth at the largest scales, and the only thing big enough are the jets.
So they're affecting their galaxies and actually maybe turning off star formation?
Yeah, so they're heating the gas, and stars actually need the cold of space to form, and when you heat it up to see X-rays, you're going to end up basically truncating this process. But you know, we don't actually have an end-to-end model of how the black hole is powering these jets, how the energy is released, how it's channeled into different forms. And I think now we're going to really be able to nail this problem. And that's why I'm excited.
Understanding how the jets are created is just one of the many ways in which the EHT project and this first amazing image may help us reveal the processes that power supermassive black holes. Well, that was spectacular. I confess I thought we might be disappointed that we'd get an image, but it would show a blur or just a blob. But instead, what we've got is one of the iconic astronomical images. To see the shadow of a black hole for the first time is really quite something. It's important to remember this is just the beginning. They've already got data from the centre of our galaxy. They've got another year's worth of data looking at M87, and so this is really just the beginning.
That's all we have time for in this programme. But do join us again next month when we start the countdown for the 50th anniversary of the Apollo moon landings, with a programme all about the latest lunar science. Until then, good night.
Waxing, waning and full. Learn more about our closest celestial neighbour in the Sky at Night Book of the Moon, available now. Tomorrow at 25 past midnight, the likelihood of living celestial neighbours investigated. The search for life, the Drake equation.